There we go. Well, good evening, everybody, and welcome to Global Math Department. My name is Jessica Bogie, and I am your host this evening. Tonight, we're going to hear from Dave Martin all about math, and everyone is welcome and everyone belongs. Before we begin our session, I did want to explain a little bit about how the Global Math Department goes. We are an organization that is run solely by volunteers. So to keep our free, high quality PD, we usually reach out and look for webinar speakers, webinar hosts like me, people that will write for our newsletter. Our newsletter writers are normally people that are sharing about an area of math or teaching that resonates with them, that they're interested in or that they're passionate about, or they discuss recent math blogs that help teachers reflect on their practice. If you would like to volunteer or know someone who would be great in any of these areas, please have them email us at globalmathdepartment@gmail.com or have them reach out to us on Twitter. So let's get started with tonight's webinar. 1 second. All right. It's always fun when you've got dogs and they're realizing that they didn't eat their dinner yet. So before I introduce our speaker, I want to explain how our meetings work. They are recorded and are available typically about 24 hours after the meeting ends. So to view the recording, all you have to do is go to the same link you used to get here tonight. That also allow you to share that link with other people that you want to share the presentation with. So the Global Math Department community prides itself on being friendly and supportive. The chat room is available for topical and general conversations throughout the meeting. Our presenter and myself will help catch questions to make sure that they are addressed either during or at the end of the presentation. So why don't we, I saw some of you were introducing yourself, so why don't you share where you're from if you have not already, and let us know where you are watching from and what you teach. Yeah, some people all over. Thanks for joining us. All right, so it is that time, and our webinar speaker is Dave Martin. And a little bit about Dave before he gets started. He has a master's of mathematics, a degree in education, and has a love for prime numbers. He has been teaching for 12 years, during which time he was nominated for the Teacher of Excellence in Alberta, has spoken across North America, and has successfully removed grades in most of his high school math courses. Dave has taught grades 6 through 12, was one of the division's math science lead teachers, and is now currently a vice principal of a K-9 school. Some of his passions include playing board games, solving puzzles, and reciting the digits of pi, starting at the end. Nice. I like that one. So thank you for being willing to present to us, and it is yours.
Oh, thank you. Thank you. Well, thanks, ladies and gentlemen, for spending your evening with me. And I hope we're ready to have some fun. And I hope you have a piece of paper or a pencil or something around you, because we're going to do some crazy math. And I want to start at something that's really, really important to me that I used to, as you heard, was a kindergarten to grade 12 math lead. And I learned something very, very quickly, that elementary math is anything but elementary. And we're going to do this right now, but even something just so simple as this. So just to imagine for a moment, you're driving to work, and you're driving to work at 50 kilometers an hour. So I'm going to give you a simple math problem. And you're driving to work at 50 kilometers an hour, and you get to work, and then you realize, oh, man, you forgot your wallet, your purse, your credit card, whatever it is. You forgot it at home. So you turn around and you zip home at 100 kilometers an hour, at 100. So you went to work at 50, forgot your wallet, and then turned around and went back at 100. What would be your average speed for this journey? Can you just write in the chat what you think your average speed? 50 there, 100 back. What's the average speed? Give you 30 seconds if you just want to type it in chat, what you think the average speed of this trip would be. What does your gut tell you? Okay, so I'm seeing Yeah, good. I see a 75 and immediately not 75. Good. It's not 75. And most people, when you ask this question, they think, well, the average of two numbers is just add them together and divide by 2. Because we teach this a lot, that averaging. But of course, with speed, it doesn't work this way. Something so simple actually has a very, I think, beautiful answer. Because you spend more time going 50. In fact, twice as much than you do doing 100. So as it's actually 200 divided by 3, not right? Because you would take twice as much. And so, yeah, it's very interesting. And so something so simple that has a very, I don't know, a really, really crazy answer that most people would get incorrect. Now, what I want to do is we're going to change the rules because we're going to do elementary. You're going to come with me for the next 20 minutes or so on a journey, and we're going to learn how to count. So you're going to go from kindergarten till about grade 6 with me in about 30 minutes. And I'm going to show you how, just right off the bat, this kind of early elementary mathematics is a little more difficult than you think. So I want you to hold out your fingers. If you're not, just look at your fingers, and you can see on the screen there we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I don't know if you noticed why we call this 10, but there's something very interesting about the last number that's different than all the other numbers. Something very interesting. And you'll notice that the last number 10 is 2 numbers in it, or 2 digits. And it means that because as we know in kindergarten, in grade 1, that 10, the digit in front of the 0, is a tens digit. Huh, interesting. Now, what we're going to do, though, is we're going to change the rules. So for the next 23 minutes, we're not going to be Earthlings, ladies and gentlemen. We're going to Mars. Okay, we're going to Mars. So wherever you are right now, what I want you to do is imagine, if you can see on the screen here, you don't have a pinky and you don't have your thumb in both fingers, both hands. Sorry, my apologies. So all you got is this. All you got is these. Now imagine now you're in my kindergarten class, and these are our fingers. We only have 1, 2, 3, 4, 5. But remember, we're going to play by the same rules of mathematics, meaning that because this is all I have, when I'm showing you this, this would actually be a full set of things. Those Earthlings call it, as they would when they show all their fingers, 10. Because think about this. 10 is simply showing all the fingers I have on my hand. So as Martians, we would count as 1, 2, 3, 4, 5, 10. Hopefully that makes sense. And so from now on, for again, the next 22 minutes, we are now Martians, and we have no access to the pinky or thumbs on our fingers. And we're going to see just how difficult or maybe tricky elementary math may be. Or maybe you're like me and you'll find it just as beautiful and joyful as everything else. So what I want you to do is in the chat, what number would that be in Earthling, or not in Earthling, in Martian form? What number is that? I see a 3, then another 3, and then a third 3. Now, I know it's not 9 because those Earthlings would call it 9, but we don't have the number 9 in our world. We only have 1, 2, 3, 4, 5, and 10. And of course, 11, 12, 13. We only do the digits 1 or 0 through 5. Good. I see Melissa. Melissa's awesome. Yeah, you guys are wicked. 13. Of course it's 13. It'd be 13 because the first 2 sets of 3s is our full set, which is 10. And then we have 3 more, which is 13. Cool. So now think about this. Think about this. So you're going to count with me, grade 1s, awesome group. We're going to skip count. So imagine you're all on my little wonderful carpet in my math class. And we're going to skip count here by 3s. And so wherever you are, you can say it with me. First one would be 3. Now remember, it's not 6. Those crazy Earthlings would say 6. But us Martians only have the numbers 0 to 5. So we'd have 3. Then it's a full set now. So it'd be 10, 13, 20, 23. So that would actually be the number 23. Why is it 23? Because it would take, in a sense, 2 full Martians' hands. Yeah, Adina, I hope I'm saying that right. Yeah, you guys are all, oh, I'm in the enrichment group here. The chat's just is, yeah, you're all correct. So now let's count by 2s. Let's count by 2s, grade 1s. 2s might be a little tricky. I don't know. Let's try it. I don't know if you can see my mouse. Can you see my mouse as yeah, I think so. Okay. So this will be 2, 4, 10. Remember, 10 is just really what those crazy Earthlings would say 6, that weird number, that weird phrase. But for us, it's 10. So 2, 4, 10, 12, 14, 20, 22, 24, 30, 32, 34, 40. So that's the number 40. Perfect. Perfect. Great. So what I want to know is this. Can you write in the chat, what question am I asking and what's the answer? What question am I asking and what's the answer? So what's the addition problem? What would be the answer to that? I feel like Genevieve and Adina get 100 gold stars for answering all the questions correct so far in the chat. Now, what you might see is, yeah, we see, okay, so these earthlings and us would count this number the same. This would be 4. And of course, this would be 5. Now, you'll notice something very interesting. Those earthlings might call this a 6 frame. But for us Martians, this is the 10 frame. And if you probably thought of maybe, if I just take this dot and move this over, I now got a full set of things. So in a sense, this is 10. And I have 3 left over, which would be 13. So hopefully you could see that 4 plus 5 is 13. Okay, try this. What's the question? Here. Or what's the answer? What does your brain do to figure out what the addition or the summation will be? I see 5 dots, then another 5 dots, then another 5 dots, and then 4 dots. So I see it's 5 plus 5 plus 5 plus 4. But what would be the answer to that summation? Now, I see 31. Let's check it. Now, what you might be doing, and I don't know, really helped me when I'm looking at this question, is to kind of visually move these dots around and fill up these frames. Of course, these are 10 frames, as normal Martians. Those crazy Earthlings would call it 6. But you can see I have a full 10 frame, a full 10 frame, a full 10 frame, and 10 plus 10 plus 10 is 30, plus 1 is 31. Nice, Adina, brilliant. Great, exactly what she said in the chat. That's awesome. So we have 41. Now, humor me now on answer one of those questions. Answer one of those questions. I'm going to remove the dots this time. I feel like we might be flying through this one. You guys seem very amazing Martians. We're in about the end of grade 1, ladies and gentlemen. So 1 and 3, I mean, if I was a Martian, I could show you 1 and 3, and it's still using my fingers. As Adina said, this would be now 4. If I go 4, which is now 4 in my hand, and I add 2 more, I'm at a full set of fingers. That's 10. Good. And Melissa's right, 5 and 4. Now 5 is really one number away from 10. So I'm going to take 1 from the 4, put it into the 5, making a 10 plus 3, and give me 13. That's awesome. Okay, one more. Pick one of those questions. Or you could pick the challenge question. What are 3 different numbers, 3 unique numbers that sum to 40? So you can pick the super challenge question or pick which one. If you're still kind of struggling, just think of, you can draw some 10 frames. And I'm going to ask does anyone know how you might do, or can you explain how to do the last one? What's 33 plus 24? Now, Adina, interesting. Adina says 61. But remember, us crazy Martians, or us regular Martians, don't have the digit 6. Those crazy Earthlings have 6. But we only have access to digits 0 to 5. Right, we have 0, 1, 2, 3, 4, 5, and then we'd call this a 10 using the digits 1 and 0 again. It's tricksy. I know what you're thinking. This is awesome date night stuff. Hey, you're bored at home, date night. Try some Martian math. Now let's see if I can switch this over. I want to look at 33 plus 24. Does anyone feel comfortable? I don't know if they're allowed to unmute themselves or can they write in the chat of how you would add 33 and 24. And I'll try to switch it and write on. Can anyone write out how they add 33 and 24? Okay, sorry. No, we do not have it. My apologies. This is what a good presenter would have done, is ask that question before the session, just so you know. Okay, so 33 and 24. So really what we probably have, hopefully you've seen, is you really have 3 10s and 2 10s. Right. So Adina, we have 3 10s and 2 10s. So imagine this is a 10 frame of 10s. If you think about it, it's a 10 frame of 10s. Brilliant. And so I have 3 10s. Oh, geez, I got so excited. I made another row in my 10 frame. Oh, okay. So you have 1 10, 2 10s, 3 10s, 4 10s, 5 10s. Brilliant. And then, yes, 3 and 4 now. If I think of these as ones, 1, 2, 3, 1, 2, 3, and I'd have 1 left over. Well, this is another 10. This is another 10. So, of course, what we can do is take that 10 and put it in there. Put it in right there. So now I have 10 10s, a 10 frame of 10s, which is 100. And I still got this lovely guy over here, so 101. The reason I say this is, okay, personally, we're going back into crazy or regular humanoids here. There's a reason I say this. There's a reason I specifically are going to break this question apart. Is because when I go into schools in elementary, sometimes we teach kids is the best way is to stack these numbers. Now imagine you're watching this webinar and we're doing Martian World, and I said to you, here's how you do it. 3 plus 4 is 11, carry the 1, and 1 plus 3 plus 2 is 10. So it's 101. I think we'd agree. Most people would be like, what just magic happened? And so I worry about that, how often we rush to this algorithm as opposed to looking at these beautiful, beautiful visualizations of moving numbers around and flexibility. And so us as Martians, we learned that very quickly. I'd be curious if anyone at home stacked the numbers 33 and 24 in the Martian world to figure out how they add it. Okay, this is a side. All right, Martians, we're up now to grade 4. You guys have been flying. You've been flying. So I want to do one other thing now with you. I know you're just as excited here. Your multiplication tables. So I'm going to take 2 minutes here. 2 minutes is on the clock. Try the best you can on your piece of paper is, could you tell me the multiplication table? So we'll do a 2 minute. And if you're at home, you can pause it. Or if you're watching the recording, obviously you just pause and see if you could figure out your 5 by 5 multiplication table. 2 minutes. Sorry, I'm laughing, Adina, because you're absolutely right. The first row, everyone goes to it, right? If you're having stuck again, multiplication is just, again, thinking of it as repeated addition. So 1 times 1 would be 1, 1. So it'd be 1, 1, 2, and so on. Give it 1 more minute. And this is not a time test by no means. And in fact, I'm modeling poor behavior where we put timed assignments on amazing math questions. Yes, Adina. Dina's already noticing some very cool properties. Isn't that 3s are the super easy one for Martians? In that those would be those humanoid 5s where we say it's really easy to count by 3s. So I'm going to show you the answer there. And there's the multiplication table done for you. And already, again, something that maybe maybe we sometimes forget to do in schools is look at this beautiful multiplication table and what are the patterns you see? Does anyone see any patterns at all? Adina's already picked out the 3s. So the 3s are like those those Martian 5s that if you skip count by 3s, you're really, because 3 is half of 10. So you'd go 3, 10, 13, 20, 23, 30, 33, 40, 43, 50, and so on. Does anyone notice anything else that's interesting? And I'll ask you maybe about the row of 5. What do you notice about the row or the column of 5s? Something pretty cool is happening there, I think. Well, I think it's cool. Anyone at all? Maybe I'll give a hint. It's very much like those humanoids tricks of 9s. I don't know if, yeah. Oh, the host coordinator. Yes. The sum of digits is 5. Because remember, 5 would be like the humanoid's 9. It's 1 away from 10. So by adding 5 every time, you're really adding a 10 and subtracting 1. So you're going to add 1 to the 1s or the 10s digit and take away 1. Yeah, Melissa. Yes, just like the 9s. Awesome. Hey, hopefully you guys, this is a great time. Yeah, this is a great time on a Tuesday. Now here's something even cooler. Perfect squares. Who would have thought the perfect squares for us are 1, 4, 13, 24, 41, and so on. Now, the whole point of this lesson so far is hopefully you might be looking at those perfect squares and being like, I don't know how I would determine the next one. Well, that might be for kids in our classes where they're struggling with actually what is the idea that's going on behind, not the idea of perfect squares. And so here's already something really, really crazy. But you guys have been great. You guys went all the way up to like grade 5, flying in 22 minutes. So let's talk about fractions. Hey, what would be a third plus a quarter? I am kidding. We're not going to do this, but this would be a really interesting task. And I hope for just the big thing here is if when I said, what's a third plus a quarter, your brain collapsed upon itself, maybe how I did when I first explored this, is it's because it's the numbering system that's causing me troubles, not the idea of summation of fractions. And I worry sometimes. I just taught grade 9 for the last year, and I saw so many kids struggle. Algebra is not the problem. It's the number sense or the flexibility behind that might be causing some issues. And that algebra seems to be the vessel that we got to discover that there is some underlying issues with these students. Hopefully that made sense, right? Okay, we're going to go back to earth. What did you guys think? Did you guys have some fun? You know what? If you're running next date night, go imagine your Martians with a 4 and a 3 on your hand. 4 and a 3. What about this like crazy Martian? This would be a 10. Oh my gosh. The possibilities. Now, I haven't really introduced myself. I know you heard a bio, but I wanted to get right into some math, so I want to tell you. But there was a beautiful what's called a introduction to me. But I can tell you honestly, this is me. I am a board game aholic. I can't drink and go on Amazon because board games show up at my house the next day. This to me, and there's something that I wanted to share, is this right here. I hear all the time that English teachers should have these literacy libraries full of books. Yet in math class, we don't talk about math. What does a math library look like? And I think here's a picture is what you're looking at right here. I have 157 board games. It's growing constantly. I'm always willing to play. I'm not saying play all these games with your kids. Don't play Cards Against Humanity. It won't go well at all. Don't leave that out of the classroom. But what I'm saying is if you're asking who I am, my name's Dave Martin, and I'm coming from Alberta, Canada. And actually the bio's a little bit old. I'm super excited. I just got a post-secondary instructing job. Prime time, it is there. Now I got to pause and find prime time because it is, or prime climb right there. I don't know if you can see my cursor. It's in the middle right. So don't worry, Jen. Thanks for the challenge. There it is there. So, but this to me is, people say like, there's a math, or are you a math person? And people all my life have been telling me this. And I'm actually not that good of math. I'm just good at playing board games. I'm good at problem solving with deductive reasoning and having resiliency. And I think this is what should be present in every single math class. Again, not these specific games. I just took a quick picture. But Killer Bunnies is, I don't know if there's, actually, I would say this. Every game you're looking at has some mathematical entity inside it. Will it help them add fractions? Maybe not. Will it help them do quadratic formulas as I saw a high school teacher was here? Probably not. But here's what it will do, is it will convince them that you're able to understand and be successful at the thing you're doing. Veronica, I 100% agree with you. What does this math person mean? I just taught grade 9, and I will tell you this, as all of your kids, and probably not all your kids, all of you with some capacity, with some student along the way, they've already been convinced that they're not going to be able to do what you're about to teach them before you even start talking. And this kills me. And so right here is a vessel of a way to get kids that self-confidence built up, that everyone is a math person and everyone can do math at the highest levels. Now, another thing is I had the luxury of working with many teachers. And this is a question I always pose to educators is which one are we preparing our kids for? If we're looking at ways to generate better test scores, better memorization, faster students, then we're really preparing them for Are You Smarter Than a Fifth Grader? But I think we can do better than that, because if that's the case, this device here, my iPhone, is the smartest person in the room. This is the thing that can calculate the fastest and knows the correct answers. What I'm saying is I think we need to go better than that. We need to become myth busters. We need to have kids challenge things, figure out, ask questions, what's happening. And I really think ultimately, yes, Juan, yes, do math and do a person. Yes, is this. This ultimately is the goal. I think this is it. I don't care if you teach pre-K, you could teach fifth year calculus. We want kids to think like mathematicians. We want kids to do what it is that we would think mathematicians do. And repetitive problems in the same sense over and over again, testing to see how fast they can do it, is not what a mathematician would do. Now, I want to show you this is that in grade 1, I asked a class, I thought, a very good math question. And I'm going to show you how easy it is to get kids to think like mathematicians. I gave every kid 15 tokens. And I said, how many tokens are there? And every single one of them had to count 1, 2, 3, 4, 5. And all I asked them was this: how would you arrange them so that the 15 tokens was easier to count? How would you do it? How would you arrange 15 tokens so that they're easy to count? What would you do? 3 rows of 5. Awesome. Awesome. Maybe you're thinking, 3 rows of 5 or 5 rows of 3 or a stack of 10 and then 5 more. But I'm going to tell you this. I don't know what you said to yourself. Maybe you didn't say anything, but whatever you thought, you're wrong. You're absolutely incorrect. And grade 1 Susan got it right. This is how grade 1 did it. She's a grade 1 student. I don't care what you think the answer is. That's the correct answer. That's the absolute correct answer. This wasn't even my goal. I was thinking of what people said, groups of 5, groups of 2. I wanted to see how well they were skip counting. I wanted to see who's going to skip count by 1s, by 2s. And Susan here, with the biggest grin around her entire face, said, what about this? And I was like, this is amazing. This is brilliant. And what erupted was, what numbers can we make out of tokens with the same number of tokens, the number we're trying to make? So can you make a 1, a 2, a 3? And what erupted is kids started coming up with, well, no, there's a lower number, a lower limit. They didn't say lower limit. Sorry, I'm a calculus guy. But they had a lower number, and they said, I think after that, any number to infinity. And then they're like, how do I make infinity? It was brilliant. What erupted was just a simple, easy question, and erupted in such a deep discussion. And I think is this. I've done a lot of research of how people can learn math and how people get to this abstract sense. And I will tell you this, that I think sometimes we skip over that middle part. We have kids playing with blocks at early ages. And oh my gosh, if you're an elementary teacher, if you are an elementary teacher, you have my billionth time respect. I got to tell you a quick story, ladies and gentlemen. I'm a high school teacher by trade. And I used to complain about the diversity in my class, how wide the walls of my classroom were. I was blind. And here's how I was blind. I went to an elementary class. I got this division role, and I got to go into a grade 1 classroom. And I'm used to these, what I thought walls were large. They're not large at all by any means, like the edges of my classroom. And in a grade 1 class, I gave every kid some tokens on a pumpkin. And I said, what I want you to do is give the pumpkin 6 teeth. Give the pumpkin 6 teeth. You can have as many as you want on the top and as many you want on the bottom, but it has to have 6. And my goal was to discover all the different ways we can add to 6. I have one kid asking for more pumpkin sheets because he wants to find out all the ways on his own. And that exact same breath, I'm looking at Jimmy, who's getting all the different ways and really playing with number theory. And I look over there, and Jason has 6 counters in his mouth. And he's like, can I get all of them in my teeth? And I realized the walls of a classroom are much larger than they are in high school. And grade 1 teachers, you do a million job. Brilliant job. My worry is as we go up into junior high and high school, we miss this middle part. We miss such the crucial opportunity that kids play with blocks, then they draw things, they visualize, and then we go to abstract. And I'm going to give you a very, very easy example. Okay, I went elementary. We're going to go a little more high schoolish, not high schoolish, sorry, upper elementary, lower junior high. What are those numbers on the screen? Can you just tell me what those numbers are? I did this in a grade 2 class, actually. The idea is not really grade 2, but the grade 2s followed it. So if I drew the numbers 1, 3, 5, 7, what are those kind of numbers? Well, how would you describe those numbers? Grade 2 kids would tell me, well, I'm missing every number. I'm skipping over every other number. And so hopefully you see 1, 3, 5, 7 they're odd numbers. They're odd. Now, I'm going to show you something that's kind of interesting in an abstract sense. And then I'm going to show you it again in a visual sense. And hopefully you can understand the illustration of how powerful visualization can be. So I take the first odd number, I have 1, not interesting. Maybe I'll take and add the first 2 numbers. I get 4. Okay. I'm going to add the first 3 numbers. I get 9. I'll add the first 4 numbers. I get 16. Does anyone know what's common about those numbers? What's common about 1, 4, 9, and 16? What are those numbers? Anyone, any ideas at all? Yeah, they're perfect squares. Now, maybe, and I'm telling you this, in grade 2 and up, when I authentically, again, the best job, I got to experiment all these questions. I gave this to grade 2. No one could tell me what was happening. Junior high kids could. But again, this is an abstract sense. I'm going to give you the same question in how I gave it to grade 2 kids, because I knew this would be too advanced for them. Is I asked them this: what numbers are here? And of course, they say the blue is 1, the red is 3, the green is 5, 7, 9, and you're adding 2 every time. Okay, interesting. Again, they didn't use the word odd, but they just knew that we're missing a number. Now watch what happens when I add 1 and 3. I get 4, and it actually makes a cool shape. I add that into the next odd number, it makes also a cool shape, and another cool shape, and another cool shape, and another cool shape. And all those kids were telling me these are perfect. These are squares. These are absolutely squares. Yes, it's a square that when I add odd numbers together, I get squares. That's really powerful. Now, of course, in junior high now, this is mind-blowing. You drop the mic and walk out. This is why when we add odd numbers, we get perfect squares. The same idea, not in an abstract sense, but in a visualization. There's a way different meaning and a better understanding of what's actually happening. Okay? Now, with this, I'm going to share with you, which I think is one of the, I was playing with this, and it's a cool activity that I played with anywhere from kindergarten all the way up to, yes, and I'm not joking, calculus, is this. And we're going to start with this. This is a dice picture I made. I just took some dice and I made a picture. You get to tell me what number you see. So can you, in the chat right now, tell me what number you see? And I'm going to model it with this. I see the number 5 just as a 5 on a dice. I see a dot in the top left, kind of a collection, or not a dot, but a collection of dice, then collection of dice in the other corner, and then 1 in the middle. So I see kind of like a 5. Just by the orientation of the dice. You might also say, well, I actually see 40 because I'm going to count just the yellow dice. So there's 10 in each corner. So 10, 10, 10, 10, that would be 40. Does anyone see another number? And tell me, just in the chat, how did you count that number? Okay, 25 groups of 4. Good. Going down the diagonal. I think there's 6 groups of 4 there. 2, 3, 4, 5, 6. Yeah. The purple is 20. Awesome. Now, excuse me. Already what you're going to notice is you give this to a class, and of course you would not give this in grade 1. This might be a little too advanced with the numbers, but you actually can see that people self-differentiate. The students who want to count by big numbers will count by large numbers, and the students who count by smaller numbers count by smaller numbers. Maybe it's someone who's just, I want to see the number 5. Well, how many ways can I see the number 5 is maybe the question I might be playing with. And so this is what's called a unit chat. Now, I got so excited about these, ladies and gentlemen. This is my Friday night one day. And this is a bit.ly. Oops, sorry. If you go to bit.ly/count for me, and you're going to see, and here I'm going to just switch you'll see a website I made. Now, I'm going to be honest, this brought me joy. It was on a Friday night. My friends were like, what are you doing tonight? And I said, I'm playing with dice. And I don't know how crazy I'm going to get. But what I did is I made these dice pictures. So I made dice pictures on just different ways of unit chats, of showing kids numbers in dice and orientation and saying, how do you see those numbers? Or what other numbers do you see? And yeah, I got so excited about this. I created these. And this is an awesome one. I had to go to a class that said, how many ways can you count by 4s and 3s? So the teacher was saying to me, Dave, my students are struggling counting by 4s and 3s. So can you make something, an activity that will help them count by 4s and 3s? And so what I did is I made this picture, hoping they'd count by 4s and 3s. Well, some jerk face started counting by 7s. He combined the 4 and 3s, and he skipped counted by 7s. So what's awesome is that it even has self-enrichment and built into these activities where you just show the number and just say, what do you count by and how do you count it? And have different ways students can do it. Now, I don't know if you have read Dr. Nikki Newton's work. Dr. Nikki Newton is an amazing research, I guess, worker, brilliant in math, where she has worked on how do we acquire multiplication facts. And I know that sometimes we just throw kids the multiplication table and kind of, and I don't mean this but rudely, but we're timesing by 3, then timesing by 4s and so on. But her research actually says this is the order you should teach it in, is times by 1s, 5s, and 10s, then 2s, 4s, and 8s, and then 3s, 6s, and 9s. And of course, the only number we're missing is 7. Well, only 7 by 7. And so I made slides, if you click on those links, that will take you to pictures that will help them in that order of multiplication as well. Now, of course, please, this is just a guide. You do not have to start in these pictures and then you go ahead and go crazy. Again, I know what you're thinking, date night, okay? Get a bottle of wine and, enjoy yourselves with these dice pictures. This is a great time. I don't know how crazy you'll get, but it's a great, awesome time. And so there's an activity that I love using. It's just how many, or a unit chat of just asking kids. Now, maybe you're teaching middle school or higher ed. And now you can do this in elementary too, but this would definitely hit some higher ed or middle school or high school outcomes. Let's go back, imagine we have now a dice chat and a pattern chat have a baby. And you could do this. Oh, I hope I didn't, I maybe ruined it. For those who are going to watch the recording, do not pause at that little moment. But imagine now I'm going to do something a little different. Joe Bowler's work does this awesome activity. I don't know if you've read her stuff. She does brilliant stuff. Is that instead of giving kids figure 1, 2, and 3 and asking them for 4, 5, and 6, what if you gave them the middle of a pattern and this? What do you think figure 1 is or figure 3 is? I made a pattern with dice, and each time I change something with the pattern the same, and you're looking at the middle figure, not the middle finger, the middle figure. What would that be? What would figure 1 or figure 3? Write in the chat. Come on, 2 minutes. What would figure 1 or figure 3 be? Figure 1 is just the ones. Cool, okay. And then so I would say figure 3 you're imagining would have 3s in them. Cool? Anyone else? I feel like I'm going to give digital gold stars to anyone who answers. Okay. Anyways, what my job here is, good. Figure 3 has 4 groups. Good. Melissa, brilliant. So here's what you want to do in a pattern chat. Is you want to make a pattern so obscure that no one gets it right. And here's why. So we're all exploring our own patterns. So I go to Melissa, figure 1 has this. What would figure 4 have? Jennifer says figure 1 has this. What would your figure 4 have? And we can all self-differentiate on how complex or simple we want our patterns to be. But then we can all come back together when I say you're all wrong, and that's the figure. It's actually a shape and space lesson as well. I'm just kidding. Well, I'm not kidding, because that's really is figure 1. It's a triangle instead of a square. It's actually the shape that's changing, not the dice. Now, I say this jokingly because in an authentic classroom, now we're all rooted in the same figure again. We all had time to explore our own patterns, so we're not bored, and now we're all exploring a pattern that no one has explored yet. So what would figure 3 be? And I'm telling you, I've heard kids, I've run this lesson many times. They use the word pentagon in a sentence for an appropriate word. As opposed to a worksheet that says circle the pentagons, we actually are going to integrate shape and space into a number chat. Brilliant. Anyways, sorry, I just sounded like I just gave myself my own high five. That was terrible. Not humble of me. This was a cool idea. Anyways, so you can look at a pentagon and we look at here. Now we want to differentiate kids again to make sure that every kid is challenged or supported in the areas they need. So then we ask simple questions like maybe what does figure 5 look like? Or what does the total number of dice, what is that? Maybe you're in high school. Maybe you're in high school and you say, what kind of regression would the total of the pips be? Pips are the dots on a dice. That's a cool little party trick. You can throw that word out there. 6 extra TikTok followers if you do. Actually, let's not joke ourselves. I haven't been at a party for years. No one invites the math guy. Anyways, or you talk about the dice or the area in the middle and so on. And so these are brilliant questions that now kids can self-differentiate back together. So, okay, the other one is a literature term. You can compare and contrast, show different pictures. And believe it or not, you could tell me the difference of the pips there without counting either of them, if you just compare and contrast. And these are, again, activities that we can talk about with kids and that have low floor, as Melissa said, low floor, high ceiling, right? This was an activity, and again, this is, if you haven't read Joe Bowler's book, oh my gosh, get out of this webinar right now and go read Joe Bowler's book. Joe Bowler, Mathematical Mindset, is amazing. And what she came with is these number talks. All I did, this is you're looking at, is in a grade 1 class, simple grade 1 class. I drew these dots on the board, and I said, how many ways, or not how many are there? And what you're looking at is a chart paper of all the different ways kids counted. But on the left side, you're seeing something very magical. When the bell went and every kid went to recess, 2 girls stayed back and asked me, hey, Dave, can we make sure we got all the ways to count to 7? And I was blown away. This is a high school permutation combination math question. How many ways can you count 7 items that grade 1 kids are playing at? I'm saying that, I'm not saying recess is not important. Absolutely, they need to go out and play. But here are kids that chose recess or mathematics over recess. And it was so heartwarming. Oh, I just exploded with prime numbers. So I'm going to show you another thing, is that if you aren't doing dot pictures, please do dot pictures at early ages. But we can get even better at higher up. We take the same idea, showing something that's kind of weird and asking, how would you do it? And I'm going to give you this one now. How would you multiply 15 and 12? Oh, and Jen, I'm going to get to you. We'll do this one question, and then Jen, I'm coming to you. I see your hand is raised. Can you write in the chat, how would you multiply that? No paper. All mentally. How would you multiply 15 and 12? The reason I asked this is I asked my grade 9s this. Now, as you're... Oh, sorry, I shouldn't talk. I will wait. I get so excited about mathematics. Oh, you don't have your hand up. Okay. Oh. No, my apologies. Does anyone in the chat? Okay, yeah. Double the 15 to 30, half 15. Look at all this. Brilliant. I love it. I love every single one of these. And now I'm going to show you what Fatima did. Fatima was a student in my grade 9 math class and has showed me something that I've never thought of with multiplication. Fatima, by the way, is grade 9. I have a master's in mathematics. I'm not saying this with bragging rights, but I'm saying is I played with math for a lot more than she has. And she showed me something that I've never thought of it. Don't worry, Jen. I will see your hand is raised. I will not call on you. But Fatima said this. I'm going to tell you what she vocally said to me, and let's see if you can follow along. She says 15 and 12 is hard, but I know 10s are great. So I'm going to take the 5 out of the 15 and the 2 out of the 12, leaving me with 3 and 6. And 3 times 6 is 18, times by the 10 is 180. That's what she said in my grade 9 class. Me and the 28 other students in the class did not follow what she said. I asked, can you repeat it again? No idea what was going on. And so I'm going to draw it out for you what she did. And this was, I thought, was so brilliant. She said, okay, we know the answer is 180. Let's see how we can get there. In her mind, she thought 15 is 12 is 5 times 3. And then 12 is 6 times 2. And she realized that the 5 and the 2 make a 10. And that's super easy to multiply by 10. And then the middle numbers, of course, 3 and 6 make an 18. So she turned 15 to 12 by 12 into 10 by 18 and got 180. Easily 7 new TikTok followers that day. This was so powerful. And it wasn't powerful if we would have just said, okay, let's do this question, and now let's do this question and this question. And absolutely, I have never thought of flexible factoring. I'm going to use that term right now. Never even heard of that. That's brilliant. But I have heard of, in polynomial sense, when we learned in high school, how you have to factor and then refactor, but I've never applied it to numbers. And a grade 9 student showed me this. And it was so brilliant to see her flexibility. Now, I'm a firm believer of this. I would rather have one kid do a problem 5 different ways than the same question 5 times over and over and over again. And I worry that sometimes we do the latter, not the former. And of course, there's always a balance. There's always a balance. But I worry that how often do we get to explore the same question multiple ways? So I got so excited about this, ladies and gentlemen. I got so drunk on this idea that I actually went to my laser cutter and I made these these stencils, and I took a laser cutting thing and I made circles, and I asked, how would you count these circles? And then I had fraction talks. How many fractions? What fractions do you see down here? And I got so excited, I put them all over my neighborhood. And I put these little things, magnets everywhere. The city called me and said it's kind of like I'm semi-littering, but they're excited because kids are posting on their Twitter page. But it was awesome in that I had kids in my neighborhood going around to these signposts on their little exploring while they go out with their family walks. And if you haven't seen this already, check on Twitter, #MathWalk. And yeah, the stuff that I got from this was so cool. All the different ways of kids counting and seeing fractions from a very, very simple task. And so what do we got? We got 14 minutes. I'm going to leave it with one more. I do think the power of visualization is so important, is that I think it can even open new dimensions. And I'm saying this tongue in cheek because we're going to do a dimensional problem. I hope that's okay. Hopefully you guys are excited. So what I want you to do is this. On your, I'm going to just hang on, go to the other slide. Sorry, first time using Big Maker. I think we're here now. Sweet. You guys excited? Good. Okay. I asked that rhetorically because I can't even hear your answers. So I want you on your piece of paper is to draw me a shape that you know has 3 dimensions on your piece of paper. Draw me a shape that has 2 dimensions on your sheet of paper. Draw me a shape that has 1 dimension. And can you draw me a shape that has no dimensions? Or can you? Is one of these a trick question? I don't know. But 2 minutes are on the clock. Can you draw on your piece of paper a 3-dimensional object, 2-dimensional, 1-dimensional, and no dimensions? Got 2 minutes, and then we'll finish this and we're done. A good presenter always ends early, especially on a Tuesday night. At probably 10 o'clock or 9:45 for some of you. Oh, Jonathan, I love that quote. Every picture tells a story. So 90 seconds left. When you're done, if you don't mind putting in the chat, I think we could probably, but what would a 0-dimensional or a 1-dimensional object look like? Or would it look like anything at all? Could you put that in the chat? What does a 0-dimensional object or a 1-dimensional object look like? Nice. You guys are brilliant. So some people tell me that no dimensions is nothing. But actually, believe it or not, it's a point. It is a dot. And here's something, again, we could explore, maybe definitely not elementary, but junior high or high school, that if you looked at the screen and I was to zoom in, and I actually, zoomed in on that picture, that dot physically would get bigger and create space. But if we are in a Cartesian coordinate system with X's and Y's, and I made a dot there, and authentically I zoomed in on this dot, the dot would not get any bigger. If I zoomed out, the dot would not get any smaller. It is a point which has no part, is a definition of a dot. A point which has no part. A brilliant, beautiful explanation in that it's a thing we represent, but takes up no space. Weird. Now, I want to show you something. Maybe you've never thought of this. But now that I know 0 dimensions has no point, or just a point, believe it or not, I can replicate the next dimension by doing the following. Just simply doubling what I drew and connecting it. And for those who said a line, you're brilliant. You're all brilliant. But this one is correct. Now, how do we make a 2-dimensional object? Well, like I said, all we do is take the previous dimension and double it. So in this case, I'm going to draw 2 lines and then connect them. And as you can see, I have this funky, it's not a rectangle. It was a weird thing, but now it is. It's a rectangle or a square. Now, if I wanted to make the third dimension, I simply draw the previous dimension. I'm going to draw these 2 lovely rectangles, and I connect them, and I get a cube. Are you ready? Are you ready? Are you ready? Hopefully. What would a 4th dimensional object look like then? If you've seen how to go from 0 to 1, 1 to 2, 2 to 3, can you draw something that goes from 3 to 4? Try it. Following the pattern of drawing it over and over again, what would that look like? Try it right now. Yeah, double it, everything. Correct. Are you ready, ladies and gentlemen? It's actually what's called a hypercube. I have had elementary kids, middle school kids, and high school kids playing with this idea. Is how does a 4th dimensional object look like? Now, I'm showing you an animation. Now, what's really crazy is that actual hypercube is a square at all times. Now, if you're wondering how can it be a square at all times, keep in mind this. You're seeing a 4th dimensional object in a 3rd dimensional space. We have no access to the 4th dimension, unfortunately. It would be like you drawing a cube on a whiteboard. It isn't actually a cube because you're drawing a 3-dimensional versus a 2. Oh, it's spinning as trippy. Wait, Veronica. Wait, Veronica. You haven't seen this yet. If that's a 4th dimension, what would a 5th dimension look like? You've got it. It's a pentaract. Tell me that doesn't bring joy or fear or confusion or curiosity to you. And here's why it's all crazy. There's not a single triangle on that entire object. It looks triangular because we're looking at a 5th dimensional object in a 3rd dimensional space. We're 2 dimensions away. Oh my gosh. It's like sleep in fear, crazy people, because there is a pentaract out there and we have no access to it. Okay? Now, why I love this is that here is, depending on what class you teach, we can look at patterning. What's the pattern here? What's the number of dots, edges, squares? And if you just Google hypercube and click on the Wikipedia, which, let's be honest, Wikipedia is amazing. Here's some cool patterning. You teach middle school, you teach high school. Your question now is, what kind of regression is this? Is this a quadratic regression, exponential, and so on? Oh, the joyful experiences. And it's awesome because every kid will either feel supported or challenged through this, okay? And even this, something so simple as this. And I've worked a lot in elementary, now middle school. So I'm going to leave at the very end with something even high schoolish to calculus. Visualization is key. I was my buddy, my best friend, Jeff. Jeff and I are playing Super Mario Brothers. I am the blue toad on the green Yoshi. I jump. And I'm telling you, ladies and gentlemen, something amazing happened. I just thought of the coolest calculus question. I paused my game, ran upstairs, and I took a picture of the screen. My buddy Jeff is like, what is going on? All I asked my calculus students or high school students was this. I am the blue toad, and I jumped. When would be the best time I jump off Yoshi? And if you've never played Super Mario Brothers again, stop what you're doing now. Get out Super Mario Brothers, the coolest classic game ever. This is on the Nintendo Switch. But anyways, if you jump off Yoshi, you can jump again and double jump. And I said, my goal here is to kill this guy. Bump him on his head. What's the best way to do it? And ladies and gentlemen, I had the most eye-opening experience of my life. I showed this picture to calculus kids. 32 calculus students to be exact, 32 of the most brilliant minds in the school, supposedly, because they're of mathematics, because they're taking calculus. Do I believe they're the most brilliant minds? No, of course not. But I'm saying is that they're all calculus kids. So there's supposedly no math. 32. 10 minutes went by before one kid said, maybe we should put an X and Y grid on it. 10 minutes went by for 32 kids to one of them to figure out we should put an X and Y grid on it. Why? Because this is the first time in 12 years of their education, they got to put the X and Y grid on a picture. It came to me very evidently that every single grid they've ever seen on any picture has been put on for them. And I know this because we did solve this problem in a class. And they put the origin in the worst place ever. This is the most useless location ever, but we ran with it and we had a good debrief after. And we talked about how terrible that choice was. But they admitted that this was the first time in 12 years of schooling they said, I get to put the origin on. Think about your textbooks. Think about your static images that you give kids sometimes that all that some preliminary work, that mathematical thinking has been done for them. That's not full fault of ours, but we have to make sure always that sometimes they get to think like the mathematician. They get to think of where's the best place to do this and so on. Okay. Now I'm going to leave you this. A good presenter always leaves 5 minutes early. If you go to bit.ly/MartinFunMath, you are going to find a website of all my curated websites, amazing activities and stuff that I spent 10 years curating while I was in my job. And so if you go there, everything that's a joyful, honestly, and I know I've said this many times, this is date night again. You're bored, get out your favorite adult beverage, go to Martin Fun Math, and you'll be like, oh my God, we're going to play with dots today. Joyful time. If you need to get a hold of me or any questions, there's my email. And if you're on Twitter, there it is. So it's 4 minutes early. A good presenter always ends early. Thank you for spending your Tuesday with me. I hope you had fun. I had a blast. Thank you very much.
Awesome. Lots of fun. Some of those are I've used those dice pictures before too. Some of my favorites, but not in the way that you use them. So now I have like more ways to use them. Anyone have any questions before we head out? Anything you wanted, you can toss it in the chat. Doesn't seem to be. Okay. Well, let me wrap up a little bit here and take care of the things that we need to do to wrap up. So thank you so much, Dave, for sharing with us. And everyone who attended tonight, thank you for joining us. Remember, the recording will be available in about 24 hours. So if you wanted to share this with other teachers in your building or other places, feel free to send them that same link that you came to tonight and you can share. Our next webinar is actually going to be on September 6th. And the session title is Play Borel, Testing Your Probability, Intuition, and Confidence. The description says, join us as we explore the game Borel and use some selected randomness scenarios to test our probability simulation. We will then explore these scenarios through simulations in both Desmos and GeoGebra. And when possible, generate coding situations that enumerate all of the possible outcomes. And it is being presented by Steve Phelps, who is a great presenter. And I know you're going to come out with a lot of great ideas, just like we did this evening. So thank you for joining us this evening. We will see you in 2 weeks, same time, same bat channel, same location. Good night, everybody.